We are going to talk about fuel cells and how it is possible in COMSOL. And before we go into the models themselves, then I want to just to go through features of the fuel cell module. What is it? What the capabilities are? And then let's jump into the models themselves later. This is the current product suite that you can see here. So it's built on the fundamental product and the COMSOL Multiphysics. So that contains all the necessary mathematical formulations to solve any sort of equations, whether it's a PD or an ODE, classical Fourier equation, or any specific. So if you want to go with linear deformations, laminar flow, acoustics, electrostatics, or heat transfer by conduction or convection, so you can use the core COMSOL package capabilities for that. And if you need some sort of specialized boundary conditions, nonlinear material models, turbulent flow, just to name a few, then you can use any of the add-on modules like the fuel cell and electrolyzer module. So it contains predefined physics interfaces, solver setups, and so on and so on. And then it is possible to compile an application. So that's where COMSOL compiler comes into place. So you can create a standalone app and you can share it with others if you like, or you can copy the application to a COMSOL server and you can share those designs via a COMSOL server, and this is a file server. And there are some sort of multi-purpose modules like the optimization, so it can be used anywhere and it can be coupled to any other physics setup. So since COMSOL is not based on any specific physics, like not based on structure mechanics, but rather on the mathematical side, it is seamlessly integrated with any other modules. So you can couple optimization to the fuel cell module itself. And there are still called bidirectional links like live links. There are some links for the MATLAB and Simulink. So if you wish, you can use a controller built up with Simulink blocks. And then you can use and run a co-simulation using COMSOL Multiphysics. And there are the bidirectional links for various CAD softwares. So you have a parametric geometry inside any of the CAD programs and import it to COMSOL. It stays in a parametric manner. You can do some calculations, maybe modify the geometry, modify your design, and then you can load back the model back to the CAD software automatically. So these are the live links. So the live stands for this bidirectional link, actually. So that's in a nutshell about COMSOL and the different modules. So today we are focusing our efforts mainly on the fuel cell module, and there are many more. If you have any questions, keep them coming. Feel free to put them in the chat or write us directly. So we try to solve them and answer them shortly. So what's included in the module? So you get a bird's eye view about this one. So different types of electrodes are included, so you can set up the boundary conditions, thermodynamics, the relevant and the necessary equations are already set up, and material properties, they are used there and they are calculated based on these equations. You can solve the models with a mass transfer or without. There are different scenarios, recommended workflows. So maybe you want to start solving your model without the mass flow, then you can extend the model's capabilities and add the mass flow and gradually increase the complexity of your model. So it's included. Then you can add multiphase flow if you wish, if you want to use, and you can also add the porous media. So it's enabled by default to solve for flows in porous medium. And we did one of the models that we are going to discuss today. So we will see how it is set up in COMSOL Multiphysics, and of course heat transfer, that's quite relevant here. So you need to take into account that one. And from the electrochemical side of the model, so it's included. So all the necessary features are inside this fuel cell module. Okay, so let's go further. Different types of these systems are available. So proton exchange or PM, they are available. So we will walk through some of these models, how they are set up and what different boundary conditions can we achieve. Hydroxide exchange, that's also possible. That's included in the model's capabilities. Molten carbonate and solid oxide, so they are also available. We had in the last one, we had solid oxides. They operate at rather high temperature ranges, more than 700 degrees Celsius, and you need a constant flow, so it cannot be used as a passive system. But if you're looking for some smaller in the range or for passive solutions, this beam proton exchange membranes can be the solution here. So we will look into some of the models. So we will discuss how it is set up in COMSOL. So these are the different types of systems that can be used and created inside COMSOL Multiphysics. So from the modeling point of view, so these are the different levels. You can see a snapshot on the right-hand side with the anode, cathode side, electrolytes in the middle, and based on you want to use mass transport or not, you can create a volumetric mesh, a volume domain, or we will set up a boundary condition for these electrodes. So we will discuss this one also. General electrochemistry, so you can solve on top of fuel cells and electrolyzers any sort of electrochemical reactions. That's also part of the module, so you're not tied into just only into the fuel cells. The name says that it's predefined, it's prepared for fuel cell simulations, but it's not just and only for fuel cells and electrolyzers. And since it's a truly multiphysics problem, creating and operating a fuel cell, you need to take into account not just the chemical reactions, what happens in the chemical side between anode and cathode side, but also you need to couple, and there's strongly coupled system to the thermal, to the heat transfer side, and for the fluid domain, so they are also there, so you can use them easily. Other features, so there are lots of built-in data, especially that are really useful to calculate the thermodynamic data, the potentials, the viscosities, different coefficients, and whether you want to include the water content or not, whether you want to include the nitrogen on the oxygen side. They are predefined and they are calculated during the solution. So you don't need to use any of your own equations, but you are not limited. So as always, you can use your own equations, your own ODs or PEDs. So if you have a special boundary condition or special electrode or electrolyte that has some specialized equation that describes the phenomenon, you can do that and you can add that to your own equation, but you can use all the built-in formulations to calculate such properties based on temperature and pressure and again cell voltage. Okay, so this is the user interface for one of the fuel cell models. And we will see this right now in action in the model. So just before we go there, just have a short look at here. So what is it? So we will start at the top. So if you need, we get some global definitions and parameters, they go there. Then we can add the component and you can add your definitions. If you want to calculate something, you can use that in the definitions node. On the geometry side, so we can include the geometry and we can import it or we can draw using the built-in sequences and built-in steps inside COMSOL. So it's prepared to build such geometries, but if you have complicated geometry, then maybe it's more convenient to use a dedicated CAD software for that one, and you can then just import into COMSOL. And then here you can see a snapshot with some of the subnodes for the fuel cell interface. There are default nodes that are already there when you open up a model, like for the H2 phase or the O2 phase. And then if you need, it's required, you can add more boundary conditions or more domain conditions based on the model setup, whether you want to add an active cooling, an active flow of materials, or maybe this will be a passive element, so maybe that's not really necessary, or if it's a thin layer because you don't want to include the mass transport, that's negligible from the modeling side, then you can replace the volume conditions to reuse them to surface or boundary conditions, so you can speed up the computation. And then that's just one part, the fuel side itself, the chemical side, solving for the chemical reactions, for the reaction kinetics and for the other coefficients. And if you want, you can go further, and here you can see the free and porous media flow is added also. So you can go and add the flow calculations to your model with the porous media applications here. And since there are more than one physics, then the multiphysics node will automatically appear. So you can combine the two physics here. The porous media is coupled to the fuel cell interface, so it creates a reacting flow coupling between the two physics. And if you want, you can extend with the heat transfer capabilities and so on. So you can gradually increase the complexity of your model, and you are still in the same user interface, but adding more and more complexity to your model. So that's in a nutshell for the fuel cell part from one of the model's user interface. Species transport. Here you can see on the right a snapshot of that snapshot from a 1D model. Some of the nodes and subnodes are visible. So you could use either the transport of concentrated species or transport of diluted species based on the content ratio of the solvent to the reactant. So you can decide whether the diluted species or the concentrated species interface is the right choice for you. Oops, too much fluid flow. Yeah, so it's possible to include the phase flow interface here. Typically, these are laminar flow interfaces. So that's the default that's enabled there. In most of the cases, that's suitable and enough to do that. And it's prepared to do more than once. So it's prepared to do two phase flows with different predefined physics interfaces. There are different formulations for different mixtures and different ratios of fluids. So you can choose for the bubbly flow, the mixture, the oil and oil phase transport. So these are the most relevant that are useful for these fuel cell simulations. And then you can also couple to porous media flow. Then when the flow goes through some porous media, and you can use any of the equations, either Darcy's law or Brinkman's equations. And yeah, of course, you can couple, since there is a flow calculation, we can couple that to the chemical reaction part. So we can create a reacting flow multiphysics node there. And it's also possible to do that. Yes, and the third branch, so we had the chemical in the fuel cell module, then we had the fluid flow. And yeah, the third relevant thing happens here is the heat transfer part. So they are also, those calculations are also included. You can add solids, fluids, and porous media to your domains depending on your needs and your boundary conditions. Yes, and actually that's a passive cell, what you can see on the right-hand side. So we will use this as maybe the second example today. So we will see how it will heat up with different fuel cell values there. And so this chemical heating is automatically added to the multiphysics node. So on top of the fluid calculations, you can add the heat transfer node there also, so creating true multiphysics node there. Okay, so here, that's the summary snapshot, what is included with the fuel cell. So from the electrochemistry side, in general, primary and secondary current distributions can be solved. Electrodes in shells. So if you want to model thin structures, so this module is prepared to do that. And of course, there are the dedicated interfaces for the hydrogen fuel cells and electrolyzers. And there are also other relevant physics like fluid flow and heat transfer. they are also there and enabled, so you can add later time to increase the complexity and accuracy and validity of your model. Okay, properties database. As I mentioned a few slides earlier, so these are important. So if you want to calculate, let's say, conductivity or viscosity or density of the materials, sometimes there are huge gradients in the temperature field and velocity and maybe pressures. Then you need to correctly calculate and accurately model these variations over, even if you are doing a stationary solution, so over these quantities. So these database and these calculations are there in the fuel cell module, so they are enabled. But of course, it can be used to any gaseous mixtures, not just for fuel cells. So it can be used in general electrochemical calculations, not limited to fuel cells. Study types, the cheapest, I mean, from the computational side, the cheapest one would be to do for a stationary solution. Then you can go for transient. Let's see how it affects and how the model of the fuel cell reacts to changes in the load. Yeah, sometimes, yeah. So the different cells, proton exchange or solid oxide, so they have different ranges, how they can react, how fast they can react to changes in on the load side. So you can run full transient simulations to look into that manner. So how the model is behaving if there is some sort of sudden change in the load. And EIS is also possible, so that's also enabled. And if you have some data from the spectroscopy, so you have some measurements, then you can import it and compare with the simulation results. And if not all the material parameters or models are available, so you can run a parametric sweep or a parameter and estimation study to figure out the missing material properties. Yeah, sometimes not all the properties are available, so you need to guesstimate something. You need to start somewhere, and then you can tweak your model to match with the measurements. Yeah, Okay, and some other possible expansion capabilities. Yeah, parameter estimation, that's one thing I already mentioned. If it's necessary, you can go for turbulent flow. Of course, you need some more computational power to do that than using a regular laminar flow. So if you have small segments, so if you have pipes where one of the dimensions is much larger than the two other, then you can extend and add pipes to your system with a pipe flow module. That's also possible. And since we can have large gradients and variations in the temperature field, we can calculate the stresses, the mechanical stresses from the thermal distribution. That's also possible. So you can add the structure mechanics. And as I already mentioned, equation-based modeling and CAD, liveling for CAD softwares, they are also supported. So there are many, many more options that you can use on top of the fuel cell model. You can extend with many other modules, capabilities based on your simulation needs. They can increase the complexity of your model to match the real world problems more precisely. So that's what we have here. Yeah, okay, so we can now go into our first model here. So here you can see a snapshot of the model that we are looking into. So we have the cathode, the membrane, and the anode. And here in the middle, we have the unit cell. So it's symmetric. So we will utilize the symmetry. So we will set up the model accordingly. And the air inlet goes into the circular plates. So we want to calculate and see the effect if we are going to increase the unit cells voltage. I mean the voltage. So we will create an auxiliary sweep on that to see how it affects our performance. Again, so these are the setups and the different parts of the plate, and air goes here in the hole in the middle. That's what is included there. So what is included? So we have the charge transport for the electrolytes, also and for the electrode. So we have the electrode reactions. Okay, and in the model, we will see shortly. So on the side, on the O2 and oxygen side, you can check which species should be included: O2, oxygen, water, or nitrogen. So you can just check or uncheck which is necessary to take into account. And there are some assumptions like, so there is no mass transport limitations on the anode side. And yes, all of this inside the fuel cell model. So that's what we are going to do. Okay, so here, these are the snapshots. So the default nodes, the value you can see a capital D. That means that's a very simple thing. Those are the default nodes. And you just extend those nodes or subnodes with other boundary conditions and features. They cannot be deleted because for the essential running of the model, they are the minimum or minimal requirements to build up a model. Okay. Okay, so we will use a stationary solver, and yeah, we will use an auxiliary sweep to change the cell voltages. Okay, and here these are the results, and yeah, we will come back later. So we will revisit this. So there are two options. Yeah, to be the blue one, so that there is limited phase transport on the oxygen side, and the green one. So if we lift up, and there is no limit on the phase transport side. So these are the different stages. And yeah, we will run and walk through the cell voltage. So we will decrease this, and we will see how the cell current density is changing. So let's jump out from here and go into our COMSOL model. Okay, so what do we have here? So let's go to the start here version. Okay, so we have the model here. So let's go back to the very top. So we have the definitions here. So if you want, we can set up the parameters here at the very top, since wherever you can click on that parameter, material parameter, or boundary condition parameter in the mesh, parameter in the study node, literally wherever you can click, that can be parameters. So you can set up these here. So these are some values that we are going to use. Then from the geometry side, we have these very basic shapes here that's used for creating the model. And from the material side, we use these. This is included in the material library. So with the fuel cell, all the necessary and basic and relevant materials are included there. So that's added explicitly here. So if you have the conductivity here set up, it's a value there, it's a parameter. And if you go into that, you can see that it's technically, it's a conductivity, it's here, and it's an interpolation function. So it comes from measurement data, and you can plot and you can examine how does it look like. So if you have some other data, you can import that table or Excel or CSV file, and then you can use your own data for setting up material properties. Or you could use like what we did here. So we can use any of the default materials from the library there. Okay, for the fuel cell interface here, you can have always look at the equation view. So you can always check what you are solving for. So you can see all the equations. So we can make sure that yes, we are in the right place. So yes, those are the equations that we are looking for and we want to solve for. The equation side. So on the hydrogen side, you can check and uncheck what is necessary. And from the oxygen side, we can see that, yeah, the nitrogen is included. And that's the plus extension that we use from the default setup there. Okay, electrolyte. Let's go over there. So we have a hydrogen side that's here on the bottom. It's set up here. So we have the humidity, that's a parameter. So you can run parametric sweeps on the humidity and you can compare the cell's performance with different humidity values. That's possible there. Okay, so we have the oxygen phase here, that's on the top. And then we have an inlet like we have seen at the boundary condition side. Okay, so we have a constant flow of oxygen here from these boundaries. Okay, and we have the electrodes. So we have the hydrogen electrode. The conductivity is user-defined function, or you can use that one from the material if it's available. So you can set up your own one. Sometimes they are not isotopes. Sometimes they are anisotropic materials. So you can use any other representation. You can go diagonal, so you can set up an isotropic material properties super easily. So go back to isotopes, so that's homogeneous, so it's the same. Okay, conductivity. These are the values. If that's not fits, if any of these not fitting your needs, then okay, always go for the user-defined value. Okay, and the same goes for the O2 phase. And yeah, and one thing is missing, so we need to add the membrane there in the middle. So here, these are the available properties. So we have the diffusion on the, bottom and the top of the oxygen, and in the middle, yeah, the membrane is missing. So let's add that one here. So we need to add the membrane here in the middle. Okay, and the water activity is the RH, if I'm not mistaken. RH, yeah. So we need to put the value. It's not 1, but it's RH. Let's put a parameter there. And technically, that's the very first fuel cell model that we could set up here. So we have the hydrogen, oxygen part. We have an inlet for the, where is it? O2 gas phase. Yeah, so we have an inlet at the top. And all other properties are used there. And we have the ground boundary condition here at the bottom. And we have the potential there at the top. This is the E cell. That's also parameter, so we can run auxiliary sweep on the cell voltage. So we will change this value and we can investigate the results there. So technically, these are the boundary conditions that we are using. So ground and the potential, and then inflow of O2 at the top. Okay, from the mesh side, so we have a swept mesh. We could always use the physics controlled if you want, if you like, but they are thin structures and you can use a very nice swept mesh. So we can go back and override the default ones. So we can create swept mesh. Yeah, it's in a logical order. So let's start with this one, with the entire geometry. So let's just clear the mesh there. Okay, and then we can run this swept mesh. Yeah, we need a quad there. Okay, no matter. So we can go back with the default ones. Yes, yeah, I forgot that we have a team structure there. Anyway, anyhow, so we can go back always to the physics control. So if you have some problems with one click, we can solve that one here. Okay, so we have this one. And from the study side, so we will go for that's a default one for this type of version. So we need an initialization step. So we initialize the phases and the distribution, and then we go for the stationary solution. And here you can see there is an auxiliary sweep. So that's parameters, any parameter that live here at the parameters node. Any parameter can be put here in the auxiliary sweep, so you can run those through from 1 volts to 0.5 with a decrease of 0.1 volts. And what's the difference between this one and the parametric sweep? Because both are sweeps. Yes, but here, the nice thing with this auxiliary sweep, that the solution of the first step will be automatically taken as the initial condition for the second step, and so on. While you are using parametric sweep, the solutions are totally independent, so there is no connection between the two steps. So that's a very significant difference between the two sweeps. And so if we go let's suppose that we already solved this in 20 seconds. So we can have a look at the potentials here. So here we can see, and we can go back to the very first stage where the cell voltage is 1 volt, and then we can jump to 0.5, and we can see, we can investigate the results there. So what happens with the potential, and we can also look at the current density, how it's changing if we change cell voltage. So we can have a very first step, which is 1 volt, put it there, and then we can step into different solutions. So we can decrease the cell voltage, and we can see the current density goes high and goes up quite significantly with at least 2 order of magnitudes. So it goes higher and higher. So that's our very first step. So that's where we arrived here. So just a fuel cell version, simple unit cell. The mass transport is included, and we can see the current distribution, how this look like. And then we can extend our model, and we can go and look for other solutions, and we can include the temperature, the heat transfer properties there. So our next model here is a passive cell. So this unit, what you can see here, so we suppose that this is a last of series connected cells. So there are several of these cells connected in series, and let's suppose that this is the very last one. So we will have a boundary condition at the bottom surface for the unit cell, and the other boundary condition will be on the top right corner on that surface, but we will see this through the model itself. So this is roughly can be usable in the sub 100 watts range. So for small devices like power banks, for example, and they can last longer than traditional lithium or lithium ion or lithium polymer batteries. They can last for weeks. And now we can investigate how does it look like in COMSOL. So how you can set up these passive models. So passive, that means there is no oxygen flow, so there is no ventilation there. Okay. And that's at the cover plate. So you can see those little holes. So they should be quite large in order to have a good reactant transport to the electrode. But the hole to solid membrane ratio is maybe too large for this structural rigidity, and so we will use boundary conditions, boundary layers to set up the diffusion layers. So these gas diffusion electrodes, they are quite thin compared to the previous version. So we don't need to, and we don't want to model volumetric mesh volume conditions. So we will use surface boundary conditions with the same level, with the same sole purpose. Okay, so let's go to our model, and next have a look at these boundary conditions. So if we go back to our library and we look for this passive element here, we can have a look at our cells. So where is it passive? Open. Okay, so this is our geometry here. So what we can see there, we have quite nice and thin layers. So we can zoom in to have better understanding. So what do we have here? So we have the same fuel cell interface. With different setups. Nitrogen is also taken into account on the oxygen side, but water is not on the H2 side. So that's a difference here. And then we have the same default nodes, one for the hydrogen part to here in the bottom phase. Let's go this way. And then we have an oxygen, and it's up. That's there. And then we have the current conductor These are the two sets here. And we have the hydrogen diffusion later here at the bottom. And zoom in. And then we have the O2 in the middle. And we have the membrane there. It's a very thin structure there, but that's our membrane, separating the two layers, the H2 and the O2 part. And since they are quite thin, so we don't want to use for these diffusion layers, we don't want to use for the electrodes, we don't want to use volume, so we can use these boundary conditions there. So there is one for the H2 part and one for the O2. So here you can see, and you can set up the thickness as a boundary condition as a parameter, and you can run, if you want, you can run parametric sweeps. You can investigate the effect of what happens if you change the thickness of this electrode. But technically, we don't need to create volumetric meshes and geometries for this particular passive element. That's quite nice here. Okay, and yeah, as you can see, there is no flow of O2 since it's a passive element, and since there are electric currents running through the model and also from the electrochemical parts, so we have some reactions. Now we included the heat transfer also, since we want to take into account and we want to calculate the temperature distribution of this passive element here. And for that side, we have the heat transfer and solids interface. We have a heat flux, so where the generated heat can leave our passive cell. And then we add also the surface to ambient radiation. So this radiation is also included. I mean, the surface to ambient radiation. So there is one mode for the cores and one for the top plate. So these are the values. They are different materials, so we have different emissivity values there to set up. And so that's technically included with the fuel cell. So if you want to use rather surface to surface radiation, so there are irradiating surfaces, they are radiating to each other, not to the ambient field, then you may need additional module there, but this functionality is included there. So that's from the heat transfer side. Okay, and if you want, so the heat transfer coefficient is just a guesstimate. But if you have if you want, you can use any of these setups and settings here. So maybe it's external natural convection. So there is natural convection surrounding your device. Then you can use these empirical equations. You can use these formulas based on the material and the property and the position and the angle of the geometry. And so these heat transfer coefficients can be calculated more precisely than just putting a scalar value there. So that's also included here. Okay, but let's suppose we have a user-defined value. So let's suppose the heat transfer coefficient is constant all over our geometry and all over the surfaces. Yeah, sometimes it's not the case, but for a first guess, that's okay. And from the material side, we have the copper. And that's one property there. And we have the steel in the top. And the diffusion layers are there with their properties and the membrane with its own property. So now we extended our fuel cell, so now we can take into account the heat transfer also. And from the ground, just to visit again, so here this is the ground, so we have the potential 0, and the electric potential is here at the top on the right side, so that's a V cell. And from multiphysics now, so we have this electrochemical heating there. So the hydrogen fuel cell interface is automatically connected to the heat transfer and solids interface. And that's it, to create a strongly coupled physical system. From the study time, we are still solving for a stationary solution, and again, cell voltage change from 1 volt to 0.4. And that's it. We have some plots here. Now then that's not a problem because we have the documentation, so we can jump back and open up the document here with a single click, and we can investigate it. So this is one solution here. So this is the potential for a certain cell voltage. Then we can see the electrolyte potential, how it's changing in the passive cell for a certain and for the same cell voltage. And we can see the temperature distribution here. You can see, yeah, so it's from the left side. So we have a ground on the right. Yeah, we have a cell voltage, and the temperature is around 90 degrees of Celsius for this different setup. So if you want, and let's suppose it's too high, then you can add, let's say, active cooling. So if you want, you can change. Based on these investigations, you can go back and you can extend the model and change the heat transfer coefficient. So if you wish, you can change the constant value there to, so we have heat flux to external forced convection. So let's suppose you have a very nice constant airflow, and then you can set up the speed, the velocity of the fluid. Maybe it's not zero, you have air, for example, or it can be a different material. And then you can revisit the temperature field, whether it's decreasing in the right amount, and then you can play with maybe you need a different material. So maybe you need to increase the conductivity of certain surfaces, or maybe this geometry is not the best for dissipating the heat away from this passive cell. So that's a passive configuration. So we extended with the heat transfer solids interface. And for the third and last model, so we can extend with the fluid calculations. So that's the most complex geometry here and the most complex physics also. So we have different compartments, different channels for the flow of the air and the H2. There are different sections for the anode and the cathode. So we have the membrane, we have the cooling channel. So it's quite complex. And let's go into our model and let's investigate what different setups are made there and how it's looking inside COMSOL. So now we also had heat transfer. Now we can go further, so we can extend the model into the fluid calculations. So we can go back to the fuel cell module, and where is it? Fuel cell, thermal management, non-isothermal. And as soon as it's opened, we can investigate the different setups there. Okay, so what do we have here? Okay, yeah, hydrogen fuel cell. We already had this, so we started with this one, with the basic configuration. So these are the domains where these properties and where these chemical reactions are defined. Okay, then we have two porous media domains, flow domains, one for the anode. Here you can see this. Go to the wireframe part. So we have a very nice and special channel configuration and geometry. Then we have an inlet here at the bottom right corner, and we have an outlet there at the other end of the channel. And we have a porous medium that's happening there. And we have the properties, the matrix properties set up here. So there are some values for the sake of these calculations. So there is a porous medium for the anode, and the same goes for the cathode side. And so we have the porous medium there also, and with different matrix properties. And again, we have an inlet on the right, and we have an outlet at the other end on the top, and at the top left part. So now we also have the media, the flow with the porous media enabled for the anode. For the cathode, means, yeah, we have some chemical reactions and electric currents going through the model. So heat transfer in solids and fluids. So we have some solid domains like previously. So we have these thin structures, materials, and then we also have fluid domains. That's one for the anode side, one for the cathode side. We have the cooling fluid here at the bottom. And we have two different solids, one for the gas diffusion layers. Yes, and as you can see, we have already seen this, that it is quite easy to set up non-isotropic material properties like here. So in different directions, we have different conductivity, thermal conductivity properties, because sometimes, yeah, that's the case. Sometimes they are not isotropic. And yeah, we have some properties for the membrane itself. Okay, and an inflow on the right sides and the outflow on the left sides of the domain. They are happening there. Okay, and of course we are solving for solving for the cooling channel. So that's at the very bottom, and that's a classic laminar flow regime, since based on the geometry, based on the size, the perimeter, and then the fluid velocity. It's still in the laminar regime for simplicity, and again inlet on the right and outlet on the left side. And now not just the fuel cell and the heat transfer, but also the flow is included, so we can set up a very nice and complex model here, and all the coupling are made under the multiphysics node. So we have the reacting flow to couple the media flow to the hydrogen fuel cell for the OH2 and H2 cells phases. We have coupled the hydrogen fuel cell to the heat transfer in solids, and the different heat transfers to the different flow domains are also coupled. Three different domains, so three different multiphysics couplings are enabled there. And from the study side, since it's quite complex, we have many physics included. That's one suggested way how you can do this. So that's one suggested workflow. Tackle these strongly coupled physics, and it's easier to debug also. That's another reason why we did this. So then that's the first step, that's the default that you need to do always. So you initialize the model, the current distribution there, then you just solve for the anode. So that's one solution. You can simply click and unclick, check and uncheck which physics you are looking for and solving for. Then you just solve for the cathode, the flow domain, the cathode. Then for the channel, that's the very bottom where the cooling fluid is circulated, and then everything is working correctly, or the CFD or the fluid flow parts are okay, then you can solve everything in one place. And of course, the cell voltage is changed as an auxiliary sweep, so you can investigate what happens with the temperatures and with the current distributions for different cell voltage scenarios. So here we have many of these, but it's very nice. So yeah, we have the membrane current density. That's one nice spot there. So you can investigate that. So that's the Z component of that vector, and we can walk through and we can see what happens there. Yeah, so cell voltage is 1, so it's rather 0. And as we going to decrease, then this current is changing significantly. And of course we could do for the cooling channel temperature, so we can have a look at how is it changing. Yeah, so the entrance, so we suppose and we assume that the cooling at the entrance, it is 70 degrees of Celsius to cool down the system, and at the exit, it goes up by roughly 3 degrees of Celsius. So that's the outcome of this one. And also we can have a look at to the full temperature contours, maybe for this one. So we can investigate the whole PEX temperature. Yeah, so the coolest part is here, 70 degrees of Celsius, where the cooling fluid enters the computational domain, and the hottest here in the membrane section, it's roughly over 80 degrees of Celsius, but sometimes it's hard to investigate. So let's add the marker here. So let's just just to put a marker there, just to have a nice understanding what's there. So put a marker for the temperature. Let's put out the maximum digester. And the maximum, because we know the minimum is 70 degrees, because that's how the fluid enters the flow. The put the maximum, include the unit, towards the frame, and maybe we can add a background color to have a better understanding. What is there? White. Okay, so that's where the maximum is happening. Yeah, so it's over 80 degrees of Celsius. So that's the last one, the third model that we wanted to work through. So that's the most complex, with the most physics included, not just the fuel cell itself, but we can also include the heat transfer, like with the passive element. So we can take into account the losses in the system, and then we can also include the laminar flow and the porous media flow. So if you have a cooling enabled, we have some constant flow of cooling fluid, then we can also solve for that one, and we can couple them together to create this complex model there. Yeah, and technically, the CFD is also used there on top of the fuel cell, since we are looking for the additional boundary conditions that are required. Okay, so that's the most complex one. And technically that was the last model and the last section that I wanted to show you.